All right. Good morning, everybody. Welcome back. New week, new opportunity to get better. Okay, so if you got all the way to this point of the course, so now it's just the final sprint. So let's see if we can finish strong here. So from now on, we will put stoichiometry on the side. And in my opinion, this next part of the course is more interesting. We will deal more with chemical bonds and properties of the compounds and atoms. Okay, so let's start with some important announcements for this coming week. For this week, I will not require any online homework. Uh, However, there will be two that will be due on next week. I will post them soon. And also no in-class assignment this Friday. Okay, so therefore, on Friday, we will meet here for the regular lecture. Okay, so we are in the middle of chapter number 7. We talked a little bit about waves, the correlation between speed, wavelength, and frequency of a wave. Also how to calculate the energy of any electromagnetic wave using Planck's equation, okay? So therefore, energy is directly correlated with frequency according to Planck. For today, let's go back and talk a little bit more about the periodic table in the first part of the lecture. And then on the second part of the lecture, I will talk about some periodic trends for the elements. Okay, starting with the periodic table. A lot of people tried to organize all the elements that were known in a table. And this table would show everybody the elements and the similarities between different elements. However, the first successful story of organizing elements in a table that made sense was reported by Dmitry Mendeleev. Dmitry Mendeleev organized the elements as a periodic function of their atomic masses. And for Mendeleev, elements with similar properties fell at the same column. Okay, so his idea was to first organize the elements as a function of the atomic masses. And then in the same column, he placed elements that he knew that had similar physical and chemical properties. So this is what Mendeleev's table looked like. So see here, each column is called a group. RO means the formula of the oxide formed. And then he went as a function of the atomic masses. So hydrogen is the lightest element. So it's where everything started. Then Mendeleev didn't know any other element that had atomic mass 2, 3, 4, 5, 6, and 7. So therefore here is all empty. 2, 3, 4, 5, and 6. And he knew that the next one would be lithium, atomic mass number 7, and then so on. And here, see that he is grouping elements with similar properties in the same column. The nicest thing of Mendeleev's periodic table was that he left spaces here, for example, 44, 68, and 72, for elements that have not been discovered yet, but Mendeleev predicted that when we discover this element with atomic mass 44, this element should go in the third column, and this element will have similar properties to boron, aluminum, indium, and thallium. Same thing for the 68, and same thing for 72. Okay, so those were not discovered at the time, but when they would discover it, it would go in exactly this slot. So let's take a look at Mendeleev's predictions for the element with atomic mass 68 and the one with atomic mass 72, and let's see how precise Mendeleev was. Okay, so starting here with the prediction by Mendeleev for the element with atomic mass 68. He called this element Eka aluminum. And the first column here are the Mendeleev predictions. So he predicted, without knowing the element, the density, 5.9. He said the melting point would be low, so that's a little bit general. This element will form an oxide with formula Ea2O3, and the chloride will be Ea2Cl6. When the element with atomic mass 68 was discovered, we know that this element is gallium. Actually, the atomic mass of gallium is 69.3. So very close prediction here. The density was spot on. Melting point for gallium is low, 30.2 Celsius. Gallium forms an oxide where there are 2 galliums and 3 oxygens, and the chloride 2 galliums and 6 chlorine atoms in the formula. So therefore, that is the that's why Mendeleev is very famous. Looking at the common properties of the elements in the same column of his table, he was able to do predictions, and actually those predictions matched really well what was found later. And that is the characteristic of a good theory. Is the good theory is able to predict things that were not discovered yet. Let's take a look at the element with atomic mass 72. Mendeleev called this element Eka silicon, predicted atomic mass 72, density 5.5, high melting point. Even the color of the element was predicted gray, and the boiling point for the chloride with Eka silicon would be lower than 100 degrees. Later on, this element was discovered and is the germanium. Atomic mass really close to the predicted one. Density almost spot on. Melting point is 947, so it's a high melting point. The color, very precise, gray. And here, very good prediction for the boiling point of the chloride as well, 86 degrees, which is lower than 100. So therefore, that is the nicest thing of his table. He used common properties to predict things, and that's the basis of the modern periodic table. Only mistake of Mendeleev was to suggest to organize as a function of the atomic mass, and we know that this is not the correct way to do it. In 1913, Henri Moseley suggested to organize the periodic table as a function of the atomic number instead of the atomic mass. And that's how we still do until today. Okay, so Mendeleev suggested the organization as a function of the mass because at the time uh, they didn't know much about the nucleus, atomic number, and protons. So mass was the only thing that he had to work with. Even though was wrong, he was able to do very precise predictions for elements that were not discovered at the time. All right, very good. So now let's talk about the periodic table that we know and the one that is accepted. So first thing, the organization is a function of the atomic number or number of protons. So we start with hydrogen 1 and go to helium number 2 and so on. All the elements in the same group, they have the same chemical and physical properties. And we know that the number of the group is exactly the number of valence electrons. Okay, don't forget about that. And the rows in the periodic table, the number of each row is exactly the number of shells, and each row is called period. So therefore, first period, we are going to have just one shell in the electron configuration. As we move down, one more shell is added. Here, 2 shells, 3 shells, 4 shells, and all the way to 7 shells. And that's the maximum that we have found till the moment. Okay, so moving down through the group, one more electron shell is always added, and all the elements in the same column or group have the same number of valence electrons. Okay, so now let's talk about periodic trends. The beauty of the organization of the modern periodic table is that we have some physical and chemical trends that are periodic. In other words, they have a behavior across the period, and this behavior is started at the end, at the beginning of a new period. Okay, so we might see a trend for the first period, and this trend is restarted when we go back to the next period. The first trend that we will talk about is the radius of each element in the periodic table and the correlation between the trend across the period and across the group. So let me quickly switch to my other screen here really quick. Okay, so first thing, the radius of an element is the result between basically the distance between the nucleus and the very last electron. Okay, so we have charges with opposite sign, therefore they will attract each other. There is a limit to that. And the largest distance between the nucleus and the very last electron, that is the radius of the element. So to rationalize the periodic trend radius, we will analyze first the trend within the group or within the column, and then across the period. So first, let's talk about the trend across the group. So therefore, we are looking at the columns, and we will move from the top all the way to the bottom. And let's see what is the behavior of the radius. Okay, so that's what I will start analyzing. So we know that once we move from the top all the way to the bottom of the column, what we are doing is moving from period number 2, 3, 4, all the way to the 7th. And each new period that we go down, that means another electron shell is going to be added to the element. So for example, if we are in the period number 2, we have 2 electron shells. And if we go all the way down to, for example, period number 7, we still have the nucleus here, but now we have 7 electron shells. 4, 5, 6, and 7. Okay, so now let's think together. More shells you add, it becomes harder for the nucleus to attract electrons because you are adding an extra shell. So you are adding electrons far from the nucleus. So any new extra shell, that will result in an increase of the radius. Therefore, moving from top all the way to the bottom of the group, that increases the radius. And the reason for that is that any new period means addition of extra shells. And that's why there is the increase in the radius. And you can go in any of the groups of the periodic table, you will see the same trend. From top to bottom, increases the radius. Okay, so now let's analyze the trend across the period. Okay, so now I'm looking at the horizontal trend. So second part of the analysis here, we are going to analyze the trend across the period. Okay, so now I'm moving from left all the way to the right. And let's see here what happens. If we are moving in the same row, the number of shells is the same. What we are changing here is the atomic number. In other words, the number of protons. Okay, and let's see what happens with the attraction between nucleus and electron. We'll get stronger or weaker. So let's start here, for example, with hydrogen. So we have one proton and one shell and one electron here. And for that, we will have an, sorry, here, let's improve this drawing. One proton and then one shell and one electron in this shell. The proton will attract the electron, and that will give us the radius. What will happen when we move from hydrogen to the very next neighbor, which is helium? Helium still has one shell. However, we added one more proton. So now we have two positive charges, still one shell, and we have two electrons in this shell. So now what we did was to add an extra positive charge, also an extra negative charge, but we kept the same number of shells. So that will result in a stronger attraction, because now we have two positive charges to attract the electrons, and as the result, the radius will shrink. Okay, so when we are moving across the period, we are adding more positive charges, which will decrease the radius. So therefore, moving from left to right in the periodic table decreases the radius. Okay, moving across the period decrease the radius because we are increasing the number of positive charges in the nucleus that are capable to pull the electrons close together. And that will be the trend for the radius. Increases from top to bottom and decreases from left to right in the periodic table. Okay, let me go back to my other screen here. All right, there we go. So to confirm that I was telling you the truth, we have here inside each box the radius for each element. The unit here is picometers. So if we take a look across the same group, we start with lithium here 152, and as we move down, we increase the atomic radius of the elements because another shell is being added. And analyzing across the period from left to right, now we are adding electrons in the same shell and increasing the amount of positive charge that will attract the electrons close together, resulting in a decrease of the atomic radius. And because this is a periodic trend, it will decrease from lithium to neon. And when you come back to the element at the very next element after neon, the trend will restart. Okay, so decrease, reset, decrease, reset, decrease, and all the way to the period number 7. If you graph the atomic radius as a function of the atomic number, that's the behavior we will observe. Decrease, go back, decrease, go back, decrease, and go back. So that's a periodic trend. And looking here from lithium all the way to cesium, you have an increase because we are looking here. So therefore, the general trend for the radius increases from right to left and from top to bottom. Okay. And basically, all the other periodic trends that I will show to you today are a function of the radius. Okay, so understanding the radius will be key to understand the other two trends that I will show you today. Okay, so before I show you the next trend here. Let's take a look and think about what does it happen to the radius when an element loses or gains electrons. So let's compare a neutral element and what will happen with the radius if this element loses an electron. Okay, what happens with the radius compared with the neutral element, or when an electron is gained. Will the radius increase, decrease, or no change? So let's think about that for a minute. You don't need to answer me, and then we will analyze together. Let's switch their screen really quick. Okay, so let's first analyze when an element loses electrons. So let's suppose here we have the nucleus, and as just an example here, we have two shells, and let's say we have two electrons in the last shell, and that's what matters for us. So looking at just the outer electrons. So this nucleus will attract these two charges with a determined intensity, and that will give us the radius of the element. If we lose one electron, for example, so now we have a situation that the number of the positive charge is still the same. We still have two shells here. However, now we just have one electron in the last shell. Now the nucleus can focus all his or its attention to just one electron instead of two electrons. So as a result, because there are less positive charges to split the attention of the nucleus, the positive charge will pull this charge with a higher intensity. That means every time an element loses electron, that results in a decrease of the radius. Okay, so we are decreasing the number of negative charges. Therefore, the nucleus can concentrate its attention to less electrons and therefore pull them together. Okay, imagine that you go to a party and you have like 10 friends in the party. So you have to split your attention throughout 10 friends, diluting it. So if three or one or two friends leave the party, so now you have less friends and you can concentrate your attention better to the amount of friends left. So that's the same idea with the radius. Decreasing the number of electrons will result in a stronger pull towards the nucleus, reflecting on a decrease of the radius. Now let's see the opposite situation when an element gains electrons. So same thing here. Now it's exactly the opposite trend. So we are going to have a positive nucleus. Let's say again, two shells, two electrons in the very outer shell. So again, the nucleus will pull the charges as close as possible. And the distance between nucleus and the very last shell, that's the radius, okay? So again, you have 10 friends in a party, so you have to dilute your attention throughout 10 friends. If a new friend comes in, so if an electron is added, so now instead of two in the very last shell, you have three. Okay, so you got one more friend in the party. So that means your attention is even more diluted. So you cannot pull the electrons close together. So the attraction between the nucleus and the electrons will be weaker. And that will result in an increase of the radius. So that is what will happen when we lose electrons or gain electrons. It's all about the ability of the nucleus to attract the charges near it. Okay, so let me switch screens again and let me show you some examples here. So here we have lithium compared with lithium plus. So 152 to start with for the neutral element. And when loses one electron goes to 76. So C is a huge change from 152 to 76. On the other hand, when electrons are added, so let's see here the case of the fluorine, started with 71. Now one electron was added, the attention of the nucleus is diluted, resulting in an increase of the radius to 133. Okay, so it's all about how strong the nucleus can pull the electrons closer. More positive the charge, more dramatic is the change in the radius. So see here, the beryllium goes from 112. When loses two electrons, that goes all the way down to 27 picometers. And the same thing when we, the opposite thing when we add electrons. So therefore, if an element loses electrons, the radius decreases. And if an element gains electrons, the radius increases. All right, very good. So now let's talk about the second periodic trend called ionization energy. First, the definition of ionization energy. It is the energy needed to remove an electron from an isolated atom in its gaseous state. So we are going to represent ionization energy by this chemical equation. So we have an element X isolated in the gas state. We are going to provide energy to this element to remove one of the electrons from the valence shell, okay? So always the changes are going to be on the valence shell. So once we removed an electron from this element, we are going to form a cation, 1 plus, and release one electron, okay? So the ionization energy will measure how easy it is to remove the outermost electron from an element, okay? Higher ionization energy means that it is harder to remove it. Lower means that it is easy to remove this electron. Okay, so let me quickly change to the other screen here. Okay, so if we think about the radius, that will give us the direction to the trend in the ionization energy. So first, let me write here. Let's analyze the trend for the ionization energy across the same group. So we know that the radius, if we go from top to bottom of the same group, the same column, the radius will increase. So for example, we have here nucleus and then radius. So let's represent the last electron here, the radius for the first element in the group. And if we go all the way down, now we have nucleus, the radius will increase. So I will represent here, for example, the last electron, and I'm reflecting here an increase in the radius. Think with me, what will happen with the energy needed to remove this very last electron, comparing the first element and the very last element? Will it be easier to remove the electron from the small atom or the large atom? Well, you don't have to think about that too much. If the atom is large, that means the interaction between the nucleus and the electron is weak. So here is very easy to pop this electron out. On the other hand, for a small atom, the attraction is so intense that we have to provide a lot of energy to remove this electron out of the atom. Therefore, from bottom to top across the group, there is an increase in the ionization energy, okay? So it becomes harder to remove the electron. Now we will think about the trend across the period. And again, think about the radius, because that will give you the direction to figure out what will happen with the ionization energy. So let's write here. The second analysis that we are going to do is the trend across the period. We know that the radius across the period decreases because we are increasing the charge of the nucleus. So therefore, if we start from left all the way to right, there will be a decrease in the radius. And again, let's think about the energy needed to remove the very last electron when we move from left to right across the period. Think about how hard will be to remove this very last electron. That is all about the interaction nucleus-electron. Farther the electron is from the nucleus, smaller is the attraction, therefore easier to pop the electron out. Therefore, it's much, much easier to remove an electron from the element on the left side compared to the element all the way to the right across the period. If it is easier to remove an electron, that means the ionization energy is low on the elements on the left compared to the elements on the right. Therefore, the ionization energy increases from left to right across the period. Okay, it's much easier to pop out the electron from larger elements than the small, tight elements. Therefore, ionization energy increases from left to right and from bottom all the way to the top. And the graph here on the bottom right corner shows how the trend changes across the periods and the groups. Okay, if you note here, the noble gases, they have the highest ionization energy. That's because they have a full octet, which means is an unstable electron configuration, and it's harder to pop this electron out. Okay, removing one electron, that's called first ionization energy. To remove a second electron, second ionization energy. The third electron, third ionization energy, and so on. Okay, and here I'm showing you how the ionization energy, first, second, third, and fourth, changes for some elements in the periodic table. Okay, so with that, that's the point that we will stop today. On Wednesday, we will cover electron affinity and then move on to the next chapter. Okay, I hope you have a good week, and I will see you tomorrow. Have a good day. Bye-bye.
Have a good day.
Thank you.
Thanks, Professor.